Welcome to the PARC Forum, and thank you for coming today. It's my great pleasure to introduce the next speaker in our lecture series today, Dr. Alex Baying. He received his undergraduate degree in applied mathematics from the École Polytechnique in France, his master's and doctorate from Stanford in the Aero-Astro department about 10 years ago. Since then, he has contributed to research at NASA Ames, then accepted the position of research director at the Autonomous Navigation Laboratory within the French Department of Defense. He's now assistant professor at UC Berkeley, and his work there has received multiple awards, in particular the Mobile Century Project, which is the predecessor to the Mobile Millennium Project, received several awards, including the 2008 Best Innovative Practice Award. Ladies and gentlemen, please join me in welcoming Dr. Alex Baying.
I assume if I press a button, something will change to my slides. Perfect. That would be the phone. That will come later. So hopefully, if the person in the room would, perfect. Okay, great. Thank you so much for the introduction, Craig. It's a pleasure to be here. My name is Alex Baying. I'm with the Civil and Environmental Engineering Department at UC Berkeley. And the project I'm going to talk about today is called Mobile Millennium. And I guess the one sentence summary is really, Mobile Millennium is a traffic information system that was created a couple months ago that uses GPS information from phones to gather traffic information and broadcast it back to the phones. And what I'm going to talk about today is some of the algorithms that are running inside Mobile Millennium and some of the challenges and successes we have had in implementing and deploying them. So I think you don't really need to live in California to agree that traffic is a huge problem, and I think these numbers are quite horrendous, both in terms of wasted energy, wasted fuel, wasted time, wasted productivity. And the truth is, even if you live in California, which is such a well-instrumented state, there are not that many options for us commuters to just fight traffic. I mean, you can call in numbers, 511, you can go to web, and look at all the traffic websites, Google Traffic or Yahoo Traffic or yourfavoritetraffic.com or whatever other website. You can look at the changeable message signs. Actually, there's a bunch of them in the Bay Area. They've all been programmed by UC Berkeley students, and usually they give you, I know I have to be careful when I pronounce this name in this vicinity, usually they give you fairly good information for traffic. But the truth is, when you look at traffic information systems in general, and particularly in the US, and it's true for the rest of the world, there's not much information outside of the major freeways. This is a map of UC Berkeley. You can see information for I-80, 580, 24, 13. None of the secondary network, the so-called arterial network, is covered by information. And the reason for this is that the data that goes into this traffic monitoring system comes from dedicated infrastructure. So I'm sure if you've driven on the California freeways, you've seen there's 22,000 of these loop detectors in the pavement all over California. They basically count cars, and they're assembled into a master system that is run at Berkeley called the PEMS system. The next generation is now wireless. It works pretty much the same way. In the Bay Area, we have toll tag readers. If you use Fast Track to pay your toll electronically, that's also used for traffic monitoring system input, cameras. But anything here, the point is it's all dedicated. It's got to be built for some application. And even if California is a very wealthy state, I guess that was true up to a couple of months ago, there's just not enough money to deploy this at a global scale. And in particular, the secondary network, the arterial network, is really where there's currently almost no information available. So I think the savior to this fact is the mobile internet, and in particular the explosion of the cell phone network and the cell phone industry on the planet. I think what's unbelievable today, if you look at the number of phones, is phones already outnumber PCs by a factor of 5. You go to places like Luxembourg, it's a factor 10 or 15. There's companies like Nokia, which produce 1.5 million phones a day, and this is just enormous. This makes Nokia actually the largest camera manufacturer in the world, okay? Because most of the phones nowadays come with a camera. In fact, this looks more like a camera than like a phone. And I think what's also amazing is, if you think about what a phone is today, I mean, obviously it's a device to call people, but a phone comes with GSM, GPRS, Wi-Fi, Bluetooth, infrared, tons of ways to communicate. It comes with Like the latest phone come with GPS, accelerometers, light sensors, camera, microphone. This slide's already outdated because now most of the phones, also modern phones, come with magnetometers. So bunch of sensing equipment. And then if you think about the computational power of this phone, which is a Nokia 95, 2 years old, it has the same computational power as the Pentium M. I'm sure a lot of you here are still remember what the Pentium is. I mean, it's not that far back. So this phone has as much power as a Pentium M, has 16 gigs of memory. So you can see all this convergence of computation, control, and sensing makes this device a perfect sensor. And the beauty is, with the explosion of phones in the world, it really makes it possible for humans to gather a lot of information that was just not available before. Just a final figure to just illustrate the enormous scales of this phenomenon. It took about 10 years to reach the 1 billion phones on the planet. You can see this kind of exponential growth. Looks like next year we're going to reach the 4 billion line. 4 billion is actually the number of toothbrushes on Earth. Okay? There's as many phones as toothbrushes on this planet. And that really gives you an idea of the scale at which we can do sensing with these things. So what is it I'm going to talk about today? MobileMillenium is this traffic information system which we've built. And I guess maybe rather than just a long talk, the best would be to just show it. So if the person in the room would be able to change back to the phone for about a minute. Okay, so what you see on the screen is what I have on the phone here. I just displayed on the screen because I think it's easier. So this is basically a color map that shows a lot of information about the main highways in the Bay Area. So you can see all your favorite highways here. You can see some points of congestion indicated by the level of color. So basically green means free flow, yellow means slight congestion, red means highly congested. And then you can see a lot of other information. For example, here you can see a slowdown at the toll plaza at Bay Bridge. If there's an accident, it will show on the screen. If you turn the audio feature on, it will even spit audio reports, so you don't have to look at your phone when you're driving. Obviously, the hands-free law is something we have to be sensitive to in California. If you want to turn back to the slides, that'd be great. So basically, MobileMillenium is this software which I'm showing now on the phone, which can be downloaded from our website for free. If you can turn back to the slides, thank you. And now the difference with other services that have emerged before is that while people drive with this software, whether they look at the interface or whether they just listen to the audio reports, they also agree, if they want to send us some information. So that information is gathered from the GPS in the phone that locates them on the map. And that is sent to us through a network provider, so T-Mobile, Verizon, AT&T, whoever you're with. And the data then is gathered by Nokia and Navtech, which aggregates the data, does some privacy-preserving schemes to make sure that the privacy of users is preserved. And then Berkeley gets it and does a lot of mathematical inverse modeling on it, which means it basically takes this data, and this data is sparse, it's for part of California, and then given the data we see, we try to compute the most likely state of traffic given the data we have. And so that's happening in real time, and then that's shipped back to the phone to the map I just showed. So basically, while we spoke, since I showed this on the phone, the algorithms in these boxes here solved a couple dozen of tens of thousands of equations to give me this information in real time, and this information is updated on the average every 30 seconds on the phone. Okay? So this is what we've built. There's really 4 layers here. This project has been going on for about 16 months now. The prototype was demonstrated in February 2008, and what I'm going to talk about today is some of the algorithms that happen in these boxes here. Now, before I do that, I want to say a couple words about privacy, because I think privacy is a very important topic, and privacy was a concern from the very beginning when we started designing the system. And even though privacy is more the work done by Nokia, I think it's very important because privacy preservation is really what will make people comfortable to want to participate and enjoy this product. So this is historically the first movie we shot. This very simple data here shows a student driving a car, picking up another student. That's where he lives. And then taking a ride on the freeway, and that's GPS data sampled at 1/3 of a hertz, no big deal. Except that you can see every traffic light violation, every speed violation. You can see where the guy lives. You can see everything the guy is doing, and that can be sampled from any phone you can get probably now for $2 with your plan when you go with AT&T, T-Mobile, or whoever. So the reason why we showed this movie to our sponsors initially is there was a lot of debate in the community whether you could ever reconstruct traffic from phones. And I think for 10 years, people have tried to do this with triangulation and trilateration, which is basically using cell phone tower information. And the truth is, if it had worked, I think we wouldn't be talking today. I think what I'm showing today would have been done 10 years ago. And so because of the attempts of using this technology to solve the same problem, which have not led to a successful industry implementation that we're aware of, there was a lot of debate in the community whether you could ever use phones to gather traffic information. I think this was an instrumental movie to show our sponsors that the position accuracy is good enough to show where your kitchen is if you leave this on in your kitchen and the signal goes through the roof. So it should be good enough to also gather traffic information. Now the problem here is that obviously you don't want to gather that information, because that information will tell someone that instead of being in your office, you're in a nightclub, or that you were at the bar, where's your driveway, and so on. So the trick is, if you want people to feel comfortable in participating to this, you have got to gather information in a way that people will feel comfortable. And so one of the concepts that was initially put together by Nokia, and they have a patent on this, is the concept of virtual tripline. And the virtual tripline is kind of a next generation virtual loop detector defined by geographical coordinates. So you can think about this as lines on the road network that will act as a trigger to the phone. That means if I'm a phone and if I'm running the software and if I'm driving by one of these lines, the phone will probabilistically sending an update to the system saying, hey, I'm a phone, that's where I am, and that's how fast I'm going. And what Nokia showed initially in this project is that if you deploy these carefully, so not in front of your driveway or not in front of the nightclub, just where you need traffic information and it's not a privacy-sensitive location, if you do this properly, basically with this you eliminate 80% of the traditional issues encountered in privacy, which is basically I don't want to be able to reconstruct a trajectory from your office to your driveway because otherwise I know it was you. And so what MobileMillenium does is it probabilistically samples anybody who has the software on. That means if you're driving in Northern California, you will basically once in a while cross this line and maybe send an update saying how fast you're going. Additional to this, we also obviously encrypt the data, same encryption technique as in your banking account, so RSA. And the data is also anonymized. Once it's received at Nokia, the phone number is permanently destroyed and not stored. That's very important. I mean, your phone number is needed because your operator, they need to bill you for whatever communication, voice or data, so that number needs to be present as part of the transaction. As soon as it's received, you don't want to store this because you clearly don't want to have this data. So this is the way privacy was addressed. And I think it's very important to mention this because there's a lot of different technologies out on the street here, and it's very tempting to gather as much as possible from people, and it's probably fine until someone gets put in jail for no reason. And then people might start thinking about these problems. I think here this was something addressed from the beginning by the very design of the system. So here's the deployment of VTLs in the Bay Area. VTLs have now been deployed all over California. There's 450,000 of them in California. There's 4.5 million over the United States. And so one of the first jobs that my students did is to figure out where to put them. And so here's the map. And obviously, you can see that the concentration of these virtual sensors is enormous and nowhere near what you had for the highways. I mean, if you superimpose the highway map, I mean, you will have a couple highways here and there. All the rest has no sensors. And so what the students did is they basically figured out a set of rules to deploy this automatically. And now anybody driving a car with a phone running our software, crossing any of these lines will probabilistically send us some updates. And so they appear as dots here in these picture, but they're really lines. So therefore, the name virtual trip lines. OK, so now I'm going to shift gears a little bit and just bring in some equations to explain a little bit what we're doing. And I think this is important to understand that in order to bring people some quality information, you have to do some math. And so a couple of slides are going to be trying to explain what we're doing here. So it's very intuitive. I mean, you can think about cars on the highway as a fluid. I mean, if you were in a helicopter and you look at all these cars, you can't count all of them. So you think about them as a fluid, and think about this fluid in terms of a density. So I'm going to call rho the density of cars. And so high density, kind of dark, low density, kind of not so dark. So basically, if you have an equation for density, which is here, that equation tells you how density evolves. So once in a while, maybe you can measure density or velocity, okay? And so the equation here tells you how, given what the density is now, it's going to evolve in the future. And now this is a mysterious function q here. And this mysterious function q in this equation is plotted here. And that's something also you can relate to, because that graph here shows the flux of cars, so number of cars through a given location per time unit, as a function of the vehicle density, which is the number of cars per space unit. So of course, if you have small number of cars, then the flux is small. And a higher number of cars, the flux is higher. The more cars, the more flux. But at some point, the flux culminates and then starts to decay as the density goes bigger. And that's when traffic jams start to happen. You know, when people start to get packed on the highway, then the flow goes lower. And when you're stopped, the flux goes back to zero. Okay? That's something that even I'm tempted to say even a Stanford student could understand this, but it's too close from Stanford. So let's choose another university on the other coast. So that's something that even an MIT student could understand. So this curve here is something very intuitive. And that's what appears here in this equation here. OK, so even if you've never done PDEs before, what these equations say is if you want to model the highway, you need the equation of the highway. That's the model of the fluid. You need the notion of initial conditions, which in general you never have. Because if I'm asking you now, tell me the number of cars on the highway, nobody knows, unless you have a satellite and very good imaging. And then you also need boundary conditions. I want to know how the highway is going to evolve. I need to know how many people are coming in. And you would be tempted to say, if I measure a certain number of cars here and a certain number of cars there, I would like to declare that's the value of the function. And unfortunately, if you do this, well, that will send you straight to mathematical jail. You really cannot do this. And so one of the contributions we've made initially was to come up with a more general formulation of the problem in which you have to come with this set of equations here. And again, the one I'm going to try to explain here without looking at the equation is, what this says is, if you tell me the number of cars in this cell is 700, maybe you can impose 700 to the equations, and maybe you cannot. And that depends on what the equation says. And so it's something which is required mathematically to make the problem well posed. And well posed mean you can guarantee that it has a solution. So it might seem like a refinement that is a bit sophisticated. The reason why you need this is highways have shock waves. And if you have driven on California freeways, most likely you have experienced a shock wave once in your life. So basically, you're driving really fast, and boom, suddenly you bump into traffic, and you're driving really slow. Well, you just went through a shock wave. And what that means is the density, as a function of space, has a sudden increase. And then you drive slow with a high density for some time, and then it goes down again. So I guess that will be kind of an aerial view of what it looks like. You can see this pack of cars here. So if you're driving northbound, you bump into this big pile of cars. That's a shock wave. And then the shock waves at some point dissolves, and then it drives smooth again. Okay? So in order to be able to mathematically capture this, you need the set of barbaric equations I've just shown before, and that's just something that we need. So now, why do we need these barbaric equations in the first place? Why couldn't we just simulate all the cars one next to each other, right? I mean, what this video shows here is another tool we're using. It's called a microsimulator. It's like a gigantic software that can simulate all the cars one by one. Now, if you take a California freeway lane, it carries about 2,000 cars per hour, okay? Multiply by 5 lanes, that's like 10,000. Multiply by 24 hours, multiply by all California freeways, you can see that it's going to be very difficult to run a simulation like this. And even if you could, it would be very difficult to calibrate. So the whole reason why you need these barbaric equations is you cannot afford to simulate a whole network at this scale. It just costs too much, and it's just too difficult to calibrate. So what is the business we're in here? The business we're in here is we take data from cell phones, okay? So you can think about it as this highway, and there's a bunch of cars, and there's some of cars here like that send some data. And you try to reconstruct traffic. Now, what is traffic? How do you relate personally to traffic? If I ask you, what's the density of cars around you? It's going to be difficult to give me a number like 73 cars per 100 meters. but you can tell me very quickly how fast you're going, because that's something you can relate to. So what does it mean to reconstruct traffic? It means, given what I see, okay, given some of the measurements coming from the phones, tell me the most likely distribution of speeds around me. And you can think about it in mathematical terms as, well, there's a spatial distribution of speed, okay? Speed here is 75 miles an hour, but speed there is 35 miles an hour. And then it has a temporal variation, right? Now on 101 at university is probably 45 miles an hour, but in 2 hours it's going to be 35 miles an hour. And that changes through time. So you can think about velocity as this surface in 3D space, which represents the spatial and temporal variation of the velocity. So the business we're in today, and what you saw on the picture of the phone, is basically called nowcast, or estimation. It says, okay, you've given me a bunch of measurements in the past, and that means basically you're sampling these trajectories. And I'm telling you, given all the measurements you've given me in the past, this is what traffic looks now. That's called nowcast. And then the next stage is obviously, well, you'd like to do forecast. Like now, what you see now, and given the historical notion of demand, what will traffic be in 10 minutes, 20 minutes, 30 minutes, and so on. So our job can be summarized by this picture. We take data from the phones. They are samples from these trajectories. And we try to reconstruct the most likely surface, which is the nowcast and potentially the forecast of the velocity around us. So our contributions really fall into 4 categories. Modeling, so you need to model these things. That means you need to find the proper mathematical way to describe traffic. Data assimilation, that's the process of taking data and putting it into a mathematical model to find the most likely solution of that model given what you see. Hamilton-Jacobi equations, which is a specific model that I'm going to talk about for some part of this talk. And finally, systems, once you've done all this beautiful work, you want to implement it and just have a software that people can use for real. So this is where we're in the talk. I give this kind of lengthy introduction about what we've been doing. What I'm going to talk about for the next 10 minutes or so is one of the algorithms we've developed to integrate this cell phone data into all the other data we already have from the sensors. And then I'm going to show an experiment. Now, if you're a chemist, an experiment is you go in the lab and you mix some things and you make something happen. An experiment in traffic engineering, well, you rent cars, you pay students, you ask them to drive and carry phones, and you see what you get. So this is what I'm going to talk here. We did this in February on the other side of the bay. So that's real experimental work here. And finally, this was a very good success. So now we have a software. And so the very end of the talk will be a demonstration of how to use the software. And also, I'm going to show you what we have in the kitchen. And it's not available to the public yet, but to give you a preview of what will be in the phone, hopefully in a couple of months. OK, so now I have to do 10 more minutes of math, but then I promise no more equations. OK, so this very nice model I've shown before is good, but the problem is cell phones do not measure density. Okay? Until we're in a Star Wars type setting where you can see all your neighbors and you can compute where they are and you can see the density of people around you, cell phones today cannot measure density. They can measure position, GPS, and they can measure velocity, so that's the data we have to use. So because of this, we have to use a slightly different equation that is called the label equation. It's a Hamilton-Jacobi equation. So think about it this way. You have a road, and there's people coming in. And you give it numbers. So the first guy comes in, number 1. Second guy comes in, number 2. Okay, and then you let these numbers evolve. Okay, so you can think about these numbers as a staircase function. Okay, guy number 3, guy number 4. This is where the 7th guy is. That's where the 8th guy is. Okay, so very simple thing that even an MIT student can understand. Okay, so this equation, the evolution of this equation, is governed by this equation here called the Hamilton-Jacobi equation, where Q is the flux function I've talked before. And M is the vehicle number of the car. So if you try to visualize this surface, you have the road, you have the time, and then you have the vehicle numbers. So if I'm looking at 2.5 miles and 1 minute, and I read 17, that's the car number 17. Okay? So it's very simple and intuitive. If I look here for 2.5 minutes, and I read 47, that means between initial time and now, 47 people entered the highway. Also something an MIT student can understand. Okay? Very simple. Now, how do I interpret an isoline of the surface? Well, if I take an isoline number 3, well, that represents the trajectory of the third vehicle. So the beauty of this framework is even if the physical interpretation of that equation is a bit obscure, the solution to that equation has a very physical meaning. Is if you take any cut, it gives you a number, 13. Well, that's the trajectory of the vehicle number 13. And that's something you can measure with a phone, because the phone knows where it is and it knows how fast it's going. So what we're going to try to do in the rest of the talk is try to reconstruct that surface from some portion of this that you might be able to measure with the phone. Now, I showed this to a student and he said, well, I won't believe it until I see it for real. So I had to actually gather some data from cameras on top of buildings in Berkeley and build it for real until I showed it to him. He wouldn't believe it. So this is what it looks for real life. So each of these trajectory here is basically the trajectory of a car, and the surface, if you assemble it, is basically the solution to that equation. Okay? So that's real data. If you ever drive by Emeryville, you can look up, and there's cameras on the top of the building. They've been mounted by Berkeley, and so that's what we get when we look at this. And you can see these shock waves as kinks in the surface. So these things are just not a mathematical abstraction. I mean, they really are things that you can measure in practice. Now, here's the difficulty. So our job is to reconstruct the gray surface. To reconstruct the gray surface, you go to the math department, and they tell you, we need 2 ingredients. Well, 3 ingredients. You need the equation. OK, good, we have it. You need the initial condition, and you need the boundary condition. The initial condition, that's the red. That's the initial number of cars on the highway. Now, we do have a satellite that we can use from the DLR in Germany. The problem is it only comes through California once a day. So in general, we never have the red. So already there's a problem. You try to solve the gray, but you don't have the red. And then you have the loop detectors. They technically give you the blue and the green. The problem is, in California, every day, 40% of the loop detectors don't work properly. Okay? So, and for the 60 remaining percent, a lot of the time the data looks realistic, but it's also not very good. So you can assume that you never get the red, and that the green and the blue are going to be garbage. So our job is to reconstruct the true gray without having the red and with garbage for both ends. That's a difficult job. So now, that does not include cell phones. So the rescuer here is obviously going to be the cell phone. So let's try to first understand how we do the job without the cell phone, and then we'll add the cell phone. So I promise this is the last digression into mathematical brutality, and then we're going to try to come to a more civilized part of the talk. OK, so if some of you have learned control theory, there's a very simple concept in control theory, which is usually linked to, historically, to missile guidance. So if you have a target, and if you have a constraint set, and if you have an equation for your system, there's a set of points that can reach the target without leaving the set. For example, that point cannot reach the target without leaving the set. But this other point here can reach the target without leaving the set. That point here is said to belong to a mathematical object called a capture basin. Okay? The capture basin is the set of points from which we can reach the target without leaving the set. And the capture basin has a very nice property called the infomorphism property, which says that if you have one target, you have one capture basin. And if you have another target, you have another capture basin. And if you want to compute the capture basin of both targets, it's the union of the capture basin. Because if I have one target and another target, I can reach the union by either going to one or the other. So it's a very simple property. So this property can be used to solve the equation in the following way. You take the green garbage and you define a target above it. You take the red garbage. No, you don't have the red. So you take the red if you had it. You declare above it a target. And you take the blue and you take the above it and you declare a target. Then you construct a system, which is shown here. It involves a mathematical object called the Fenchel transform of the flux function. And you ask in this virtual world, what is the set of points that can reach any of these targets? That point, for example, cannot, because it goes below the box. But that point here can, because you can see it meets the blue target. And because the targets extend infinitely in this way, you can see that if you're high enough, you will be in the target. And you can prove mathematically that the lower part of the points that can reach the target is the solution to your problem. So the proof is 30 pages long. I can't go through it in this talk. But the result is fairly simple. All you need is to compute the capture basin of all these targets. And the lower part of that set is the solution to your problem. That's what this equation says. The beauty is, if you give me a target, I can compute a solution to the problem. If you give me another target, I can compute a solution to that second problem. If I take the union of the two targets, if I take the min of the two solutions, that's the solution to my problem with the two targets. That results from a mathematical property called the infomorphism property. Now you can see why this is very helpful for what we're doing, because we're constantly running the algorithm. And we don't want to be resolving the problem all the time. So every time there's new data coming in, I will solve the problem for the new data, and I will take the minimum of the solution with what I had before. And that will give me my new solution with my new data. And that's how I'm going to merge the cell phone into this. So that's just a mathematical statement of what I said. So now here's the cell phone. So I don't have the red because I don't have a satellite all the time. I have erroneous data for the green and for the blue. But now I have some cell phones that might be driving by today. So the cell phones, as we said before, they are isolines of this surface. I can also declare them as targets. So I have my classical targets, and then I can say now my cell phone itself, I'm going to make it a target, because I know something here. I know that's a cell phone moving, and I know where it's going and how fast it's going. So you can see why that is helpful, because you never have the red. You have very noisy data for the green and the blue, and you have very accurate data for the yellow, except the yellow comes once in a while when someone's driving by, not all the time. Okay, so what this mathematical framework enables you to do is to put all of this together and compute the most likely gray given all you see, which is the green, the blue, the red, and the yellow. So this is how we mathematically pose the problem. I'm going to explain this in 3 minutes. And then we're going to see how to do it in practice with students driving cars to demonstrate that things work well. So data by nature is not perfect and sometimes self-contradicting. So the blue guy will say, hey, I saw 2,000 cars driving by. There's no way you can have seen less than 1,000 unless there's an accident or something. So the blue guy says this, the green guy says that, and the difference between what the blue and the green says has to be bigger than the initial number of cars on the highway. That's what the math says. Now, the green guy says, hey, I saw 8,000 cars go by. There's no way you could have seen less than 10,000 coming in the last hour. So the difference between what the blue says and the gray says can also be cast in an equation. Now a cell phone comes by and say, hey, this is where I am. That's how fast I'm driving. Then the blue will say, oh, I can count cars. There's no way you can be user number 2017 today because of the people I saw before. So there's another mathematical relation between this, which says, given what the blue guy sees, the number of the cell phone cannot be less, or bigger in that case, than 2017. So there's no need to go into the detail how you build these equations, but I think you start to get the picture. Basically, by putting all of this set of equations together, you can build this set of constraints between what you see. And for example, here's the last example is, okay, there's two cell phones driving by, and they have a number. You don't know them. But because they're that far apart, there's no way the difference between their numbers is more or less than a certain value. So you build all of these equations, basically assimilating the data you have. And now there's something very striking that appears. So for this, you need to understand the concept of linear versus nonlinear, but that's relatively simple. Anything in gray here is nonlinear. That's the solution to my equation. Anything in red, that's what I don't know. That's the number of cars on the highway. That's linear. And anything in yellow, that's the number of the cell phones, which I don't know either, but that's linear. So basically, in everybody's language, all the mathematically difficult part of the problem is in the gray, and that can be computed analytically from the data. All the stuff you don't know, the initial number of cars that you would need a satellite for, and who is who on the highway, that appears linearly in this set of constraints here. And one of the basic things you learn in optimization is a set of linear constraints in a linear program is something that is very easy to solve. And so basically what I have done, I guess the summary of what I have done is I have put all the mathematical difficulty and all the nonlinearity in these equations, which I can compute analytically with the data. And I've put all the unknowns outside of it, and I have made them appear in a linear manner, which is really the contribution of how this is a very easy way to now solve the problem computationally. So now let's make it work with students, and then I'm going to solve this numerically. But now let's explain how we, prove it works in practice. So we did this proof of a concept called Mobile Century on February 8th. It was not too far from here. It was in Union Landing, so across from the two bridges here. And we rented 100 cars, and then we asked 165 Berkeley students to drive these cars for 10 hours. So that's why they were changing shifts, back and forth here. So basically, they were driving 10 miles back and forth and back and forth and back and forth and back and forth for the whole day. So that's why we had to pay them, right? Because, it's a boring job. And so but the reason why we did this is this achieved 2 to 5% of the traffic on that day. Okay? 2 to 5% of the vehicles on that stretch of highway were UC Berkeley vehicles. Why did we choose that number? Well, at the time, it looked like 18 months later, 2 to 5% would be the proportion of phones with a GPS on board them in California, which is, I think, about where we are now. So this number was absolutely picked carefully to, in a sense, be a glimpse in the future of what would be the penetration rate of cell phones on the highway. While we were doing this, we also posted teams of students on the bridges with high-resolution video cameras to film cars in a way that we could re-identify his license plates between bridges. So if you look carefully, you can read the license plate number of the person here. If you can read it here, here, and here, you have ground truth travel time for that person through that stretch of highway. So it provides a completely decorrelated data set that we can use for validation purposes. So we didn't know whether it would rain or have good weather on that day, so we had to try the cameras. So I sent teams of students on the highways, on the bridges, try it in fog and rain. They hated me for it, in good weather. And so first time they went, within 5 minutes, the police showed up saying, hey, what are you guys doing? People are calling like there's some terrorist action on the bridge. So then the students showed them alleged documents saying, well, this is UC Berkeley research. And then the officer said, oh, OK, I understand. Well, next time, just wear an orange vest and a helmet. And so they did, and nobody called. So you can draw whatever conclusions you want from this. This is the vest. Unfortunately, we don't have a picture with a helmet, but they did have a helmet. So this is what the operation looked like. So it was really like back in the old days of the military, running a kind of a field operation with 200 people in the field, releasing the car in real time, equipping them with one of these phones in each of the cars, installed by the Nokia people. I had my good friend Osama, he's a former colonel in the Egyptian army, was running a command center just in charge of security, just to make sure that, well, nobody gets hurt or just tries to drive away to Mexico with the car and the phone or something. So this was the command center, and then the teams on the highway, on the bridges, were filming the whole thing. And while we were doing this, we held a press conference with Bob Iannucci, the CTO of Nokia at the time, who came in from Finland for this, and then Randy Iwasaki. He's currently now the director of Caltrans. And we invited journalists, and they could see basically a real-time reconstruction of highway traffic flow using the cell phones. Basically, these 100 cars driving around with the phones, sending data, running the algorithm, and then it was shown in real time on the display. Now, something happened. At 10:30 in that morning, we're all looking here. The journalists are filming, and it's all great. The finger of the guy is where we are on the map. And you can see about a mile north, there's this big red thing here, like a big shock wave. People could see through the tent and could see, well, I cannot believe that at 10:30 in the morning, when people are going so smoothly, there's a mega traffic jam 2 miles or 1 mile north of here. So they started to look at us funny, and I thought, maybe this is the end of the project. There was a bug in the algorithm, or, this is it, we lost it. Well, it turns out that there was a 5-car pileup accident, and that had created this mega traffic jam, and we happened to catch it before the police and before Google Traffic and any other traffic provider. In fact, that person here, what she does is, I believe she works at traffic.com, and what she's doing on the picture is basically calling to get a traffic report from their headquarters in Wayne, Pennsylvania, to confirm the traffic jam. And in fact, a couple of minutes later, all the pagers of the Caltrans people who were there started ringing because they get an automated text message every time there's an accident. So over a couple of minutes, he realized, wow, that stuff is working really good. And of course, now the legend at Berkeley is we created the accident on purpose to demonstrate the technology. And I cannot comment on this. So if you had been in an helicopter during the experiment, this is what you would have seen. Each of the little dots here is one of the cars. The color, these guys, they're lost. They look like they missed an exit. Each of the cars is basically represented by the point, and then the color represents the speed. So red is congestion. You can see the traffic jam here, northbound, and then green is free flow. Now, I'm showing this movie for 3 reasons. The first reason is to illustrate that this data you see here, it was never sent to the system. It was stored on the phone. We don't use that data. Of course, you don't run a 100-car experiment with 200 students in the field every day, so it's too good to just let it go. So we had a special build of the software to just store it forever, because that data is very valuable. The second reason why I'm showing this is 2% of traffic is not that much. I mean, you open CNN in the morning, you'll see traffic in Bay Bridge this morning, 45 minutes, and then you see this picture with thousands of cars. I mean, 2% is ridiculous. And the third thing is, we don't even need all this data. We only need a subset of this data sampled by the VTLs. So the reason why I show this is really to show that you don't need a lot of people to participate for this to work. Now, I promise this is the last time I show these horrible equations, but we still need to finish solving the mathematical problem here. So if you remember what these horrible equations said, they said, these are the constraints that your variables must satisfy given what you see. Now, if you solve this, you could say, tell me the largest possible number of cars initially on the highway given what I see. That's what it says, maximize. Or tell me the smallest possible number of cars on the highway given what I see. That's what this other problem says with minimize. And then you can do the same with all the other parameters. So basically, if you solve this problem in various ways, it gives you guaranteed bounds on what the system should be given what you see. Now, we applied this with the data I just showed, and this is what you get. So you have the site experiment, and let's assume we only have 2 detectors in the pavement, one at the very beginning of the highway, one at the very end of the highway. And we're interested in plotting travel time as a function of time. So this is time, 11 in the morning, and this is travel time. So if this says 3,600, it means it takes 1 hour to travel through that section if you enter at 11 o'clock. Okay? That's in seconds. Now, here's an interesting thing. The accident happens right here. So the sensors, they cannot see the accident, obviously, right? Because the accident doesn't happen on the sensor. So the sensors, they're very smart. They manage to try to extrapolate what they see to understand the travel time, but they completely miss the accident because there's no mechanism to do that. So the sensor says, well, 11 o'clock, 11:30, 12 o'clock, it takes about 300 seconds to go through that section of highway, about 5 minutes. Okay. Obviously, there's an accident, so that's not the case. Now, the algorithm says, wait. You saw 10,000 cars entering. I only saw 2,000. So if you do the math and you solve the problem, it says there's 8,000 people stuck in there, and that shows up in travel time. There's no way your travel time can be smaller than this. And if you solve the other problem, it says, and by the way, there's also no way that travel time can be bigger than this, because I still see people coming out. So you can see, and then the little dots here, they are the video camera data. They're the ground truth. That's the guys on the bridge measuring the travel time for good. So you can see it's a very interesting thing. The sensors completely miss it. And that's OK. They're not designed for it. The algorithm on the sensors at least detects something, because it says, well, guys, there's no way you could travel that section as fast, given what I see. And it turns out that the truth is, yes, in the bounds between what the smallest and the highest value should be. Now, add the cell phones to it. Okay, this doesn't include cell phones. Now, add the cell phone information to it. Of course, it shrinks the range. Now, if you add the cell phone to it, it says, hey, guys, there's no way the travel time could be smaller than this, and there's no way that the travel time could be bigger than this. So it gives an even better estimate of what the range should be. Now, there's an interesting thing here. Not all points are in the guaranteed range. Now, there's a lot of explanations why that is. Well, first of all, there's French drivers like me who drive very aggressively. It's not encompassed by the model. The second thing is the model doesn't encompass people driving past each other. The model assumes people don't pass each other. There's a certain proportion of actual people who pass each other, particularly in traffic jams. And the third thing is the model has also imperfections. So in a sense, what this result tells me is if you fanatically believe in the model, well, then your travel time is guaranteed to be within these bounds. But the truth is, well, the model is not perfect, and people don't exactly behave like in the model, so not all points are necessarily in the range, but still, for practical purposes, you can see that the range gives a much better estimate of what travel time is. And at the end of the day, what is travel time? Obviously, it's a distribution, because everybody drives differently. So what you're trying to capture here is a mean and potentially a covariance. And then what we've shown is that, well, these ranges are doing a fairly good job at encompassing them. I'm going to now talk for the last couple minutes of the talk about what we're doing and how you can participate and how this can be hopefully of use to the state. But before that, I really want to show this plot because I think it's very dramatic, and I think it's also there's very few instances in transportation engineering where you can capture it so well. So this shows the trajectories of the cars during the accident as a function of time. Each of the blue line here is the trajectory of a car along the road. You can see, so for example, here this guy is driving really fast, and then boom, he hits the traffic jam. So then he's progressing slower and then faster again. Okay? So you can see this shock wave propagating here. So the reason why we go through all this difficulty of understanding these mathematical models is the mathematical models tell us how fast the shock wave propagates. And that's very important because the duration when the shock wave is sustained and the time when it's going to disappear is something that we need for your commute. If I'm this guy and I'm going to be delayed by 15 minutes, I'm better off taking off and then going to Starbucks, having a coffee, and then hitting the road again when the traffic jam is clear. But if I'm this guy and I'm going to only suffer a 2 minutes delay, I should stay on the highway. And that's what the mathematical model can tell us. So I guess in conclusion of all these kind of mathematical fireworks, something to remember is that the complexity of the traffic is something that you want to capture. And in other words, the mathematical model helps you to capture all these complexity embedded in the blue trajectories. And then if you want people to participate, i.e. if you don't want to track people from their driveway to their work, you need to do business in a way that you don't gather the blue, which, as I want to recall, was stored on the phone just for the experiment. In the current system, we don't gather it. You only capture the blue intersected with the red, which are the virtual trip lines. And so what we've done is really establish a suite of algorithms so that we could reconstruct the global information from the blue without the trajectories by just probing the blue at the intersection with the red here. And that's really key to making sure that people are comfortable to participate. I'm going to skip this, and I'm going to basically come to the end of the talk to show where we're now. So this was a very good case study, from an academic perspective, to show that it was technology feasible. And I think it was convincing enough to our sponsors that they decided to move this program forward. So in November of last year, we started MobileMillenium, named after the hopefully thousands of users who have now downloaded the software, which is a partnership between Nokia, Caltrans, Navtech, and CCIT at UC Berkeley. So MobileMillenium was initially going to be a 6-month pilot program. It's now been extended. It's open to the public in Northern California, and it's basically a free software that can be downloaded on everybody's phone. So actually, I think now is a good time for a commercial break. I'm going to just pass these around, and if you have an appropriate phone, you should definitely, so just grab one and just pass these around. So if you recognize one of the phones here, well, you should go to our website. Some of them we do support, some of them we don't, but we will support very soon. But the first step in making this work at a global scale, which is now just for Northern California, is really to make sure that a lot of people participate. Now, the second step, which is interesting, is we want to make sure that people find out about us. And so what we've done is we've done a lot of things on TV or radio or in the newspapers. So I've put a lot of my students in interviews, and of course the students love it because I think it's a nice way to value their research. But there's something very interesting that comes out of it. So you go on TV, for example, this is Elizabeth Leamy, the journalist from Good Morning America, and you get about 10,000 hits on your website. And then maybe out of these 10,000, 1,000 will try to download the software. And then 100 will successfully download the software, that we can see it. And that's not because people are trying to download it in the washing machine or anything. I mean, though some people are actually trying to download it in their PlayStation. But it's just because they don't have the right phone, they don't really know how it works. So basically, 100 people manage to download it. 10 people will use it and keep on using it. So basically, every step you go, you lose a factor 10. And so one thing that came to our attention is that I think the difficulty in making this work is that if you're losing that many people, and if people are also only participating in a very stochastic or unforeseeable manner, then this by itself should really include a lot of different tools. And so in a sense, it took $50,000 to write a mathematical algorithm on this. It took $500,000 to run the experiment. It took $5 million to build a website that is user-friendly enough that you can feel you can download it. It works on several phones. The interface is decent. But now every time you gain a factor 10, and the truth is traffic by itself is probably not a valuable enough commodity that people would change from their favorite software on their phone, Google Maps or anything else, just because our traffic is better. And so the real question here is traffic is only part of this equation. This will only take off globally if it comes with routing, with theaters near you, with satellite images, with personalized commutes, with your estimated arrival time, and so on. And so I think the question we're trying to answer now is how do we augment this set of tools we've built? In a sense, it's ironic because we're so focused on the math, on the technology, on getting it right, on having traffic information which is more accurate than this other vendor. But the truth is the success of the technology is mostly contingent on the user experience, and traffic is only a tiny part of the user experience. So I'm going to skip. We did some tests in New York, no accidents, unfortunately. But I think just to finish this, one of the things where we can really make a difference is arterial traffic. So I started this talk by saying, well, today what you really would want is this information, right? You go to San Francisco, it's going to show Van Ness, 101, 80, and that's it. So what we have in the kitchen today, and I can show you, it's not on the phone, it's just in the kitchen, is we have, so I'm going to start with Berkeley. I don't know how the bandwidth is now, so I'm not sure it's going to work. So this, what you see here, if it accepts to show on the screen, and I hope it will. Okay, what you see here is arterial traffic, real time, from a mixture of sources, which include cell phones running our software, taxi data, bus data, historical data, and loop detector data, and radar data. Okay, and so this is in Berkeley, and so today we're only showing this. This on the phone, the highway. We're not showing the rest. The reason why we're not comfortable enough at this point to show it to people is we have almost enough users that we're comfortable these results are accurate, but we want to be sure that the day we go live, it's right. Because you miss your appointment once, you miss your appointment twice, the third time you're not going to use the software anymore, right? And so what we're doing now is we're doing a final analysis so that once we are confident that given the number of users we have and given the accuracy of the models, the situation is accurate enough, then we're going to start broadcasting this. And I think today, if you look at all the traffic vendors there's very few people who are broadcasting arterial travel time or arterial traffic on their phones. And we have had it for several months. It was shown for the first time to the public for the inauguration of the Citrus building by the governor, Gray Davis, in Berkeley on February 27th. Hopefully in a couple of weeks, we will start to progressively light some of the arterial streets in the Bay Area. Hopefully also very soon, we will expand this nationwide. And so I think this is really where we can make a difference because very few people have managed to gather this information and most importantly, to put it through the proper mathematical models to extract some meaningful information for commuters. So I'm going to finish this by thanking my team. I mean, I think it's been an exciting project. In 16 months, we basically have built it from scratch, knowing virtually nothing about cell phones. And this would never have happened without the work of our director at CCIT, who is really our interface with the California Department of Transportation, which has very generously funded this work, our project manager, Joe Butler. And if you ever want to run a test where you have zebras carrying phones on the Golden Gate, he can do it. So I mean, I think this is really the guy to call. Obviously, we have a very aggressive team of software engineers, but most importantly, I want to stress out that a lot of the algorithms and the theoretical work has been done by the UC Berkeley PhD students, master students and undergrads who have really worked very intensely on this project and put all their energy and enthusiasm into it. So I'm going to stop here. I think we're right out of time. I hope we have maybe time for a couple of minutes for questions. Thank you.
Quickly, what is CCIT?
Oh, sorry. CCIT is the California Center for Innovative Transportation. It's one of the institutes at Berkeley which is focused specifically on the deployment of innovative technology for transportation. And it hosts a lot of projects, including the Mobile Millennium. Yep?
How do traffic lights fit into it?
How do traffic lights fit into it? Traffic lights are difficult because traffic lights makes these things difficult to predict for several reasons. A, when you look at the database, you don't always know there is a traffic light. And B, if you know there is a traffic light, you might not always know the cycle. the time at which it switches. So how do they fit in there? They make our life harder because we have to make more accurate models. And the sad truth is, there's very few places in the US where that data is accessible to us. If you look at traffic lights, they also have a lot of loop detectors in front of it. So technically, there is data collected to tell us whether there's a queue in front of it or not. We don't have access to that data, and we believe it will be very hard to get access to that data on a global scale because all of these systems are proprietary and owned by municipalities, cities, counties, and so on. So the answer to your question is, unfortunately, they make our life much harder. We have to take this into account into our mathematical models. I didn't have time to talk about these specific models for arterials. And the truth is, because we believe that we will never get access to this data, the phone is so far the best we have found to measure traffic around them. Yep.
So many years ago, I saw a taxi cab in Tokyo that appeared to have all his traffic in Tokyo on his screen. Was he getting that from some special purpose system? Sounds.
I'm not specifically aware about the Tokyo case. I know that in China, all the taxis in a lot of cities have been instrumented by Siemens, and I think that they're using it for arterial traffic, real-time arterial traffic estimation. In San Francisco, we have 300 taxis hooked up. We get their data every 1 minute. We don't broadcast it back, but what you see on the screen is basically the result of the taxi data. So it's basically using the same technology, except with taxis, the constraints are different. Maybe you don't really care about privacy because it's a business vehicle, so it's okay to track. And then therefore, it's good because it's predictable in terms of how much data it's going to keep sending us. And I think taxis are a very promising source of data in a lot of cities in the world. San Francisco is one of them. China has a lot of cities, New York. And in our case, any source of taxi data we will find, we will absolutely want to integrate as fast as possible. So the way it fits in this equation is, it's really, I think, one of the very promising way to collect data as well. Yep. Actually, I think you've been waiting for some time, so sorry.
Two questions. One on the mathematics. Why do you need to know the total number of cars? Isn't it sufficient to simply know the additional number of cars so that over a 25-hour period, let's say, over any rolling 25 hours, you would be able to infer or derive